Hi everyone, and welcome to our first video on our basic math refresher for economics. In these videos, we're going to go over many topics that are going to be seen throughout the course of study in a graduate program for economics. So I actually want to jump in with one of the most basic topics that we're going to talk about. And honestly, we're going to talk about this one a lot, and that's derivatives. So let's start out with the easiest thing that we're going to do in our course of study for mathematics with economics, and ask ourselves, what is a derivative? So for those of you guys who have taken calculus recently, this will probably seem pretty simple, but for a lot of people it may have been a while. So let's actually talk about this and figure out what's going on. So like I was saying, one of the most commonly used quantitative tools in economics is our derivative. I mean, honestly, we're going to use it everywhere. We're going to be solving the majority of our economic problems that we see by using some form of a derivative in one way or another. We use it for maximization in econometrics and microeconomics and macroeconomics. It's really everywhere. I mean, yeah, we use it for utility maximization, we use it in cost minimization, and honestly, if you ever hear the word marginal in an economic context, that means that we're dealing with a derivative in one way or another. So anyways, like I was saying, it may have been a while for a lot of people since they've used these skills. So I want to review exactly how derivatives work and how we can apply them in specifically an economic context. So a lot of the examples in these videos are going to be based on economic examples. So I'm going to try to keep the pure math out as much as I can. It is a bit unavoidable at some points, but we're going to try to keep this as close to economics as we can. So anyways, speaking generally, a derivative just measures the rate of change. It tells us how quickly something is changing from one value to another. But specifically, if we're getting into the details of a derivative, it's going to tell us the rate of change for a function at any given point in that function's domain. And we'll use a lot of math terminology here, but if you just remember that a domain is just all the values that x can take when x is the argument in a function. So right here I have y equals f of x, or y is a function of x. So all the possible values that x can take is our domain, while all the values that y can take are going to be our range. So the derivative is going to tell us all the possible rates of change for a function in that function's domain. Anyways, this is really important in economics because we're going to find that values are going to change depending on where we start our measurements. So, for example, in a typical principles of economics course, we teach about the price elasticity of demand, but we have to show them that if we do a simple change in price from, say, $5 to $6, and then we do the same price change from $6 to $5, we're going to get different values for our price elasticity of demand based upon where we started, just because there's going to be some degree of inaccuracy as we make those measurements. And the neat thing about derivatives is that they are able to help us solve that problem. We can actually get a very accurate measurement for values such as the price elasticity of demand. But anyways, if we're going to look at a derivative visually, we can see that it is the rate of change, and really the rate of change is just our slope. And our slope is just the ratio. It's the change in our function value, or our change in y, divided by our change in x. And remember that our capital letter delta right here, the triangle looking thing, that is going to tell us how something changes, the new value minus an old value. So basically, we're going to find that if we're looking at the derivative of a function, it's going to provide the slope of the line that is tangent to the function at point x. And I use the word tangent, we may not have heard that one in a while, but a tangency point is just a point where two lines touch exactly once. They don't actually cross, they just touch once, and they go their own separate ways. What's neat about this is that I can take the values of all of those slopes, and I can create a new function out of them, which I'm going to call f prime of x, and that's going to represent the derivative of x. So let's actually take a look at this visually. So here we have this function right here, and we can see that it starts out, it's increasing, it reaches a maximum, and then it's decreasing afterwards. So if I look at a point on the left side of this figure, we're going to see that it has a positive slope. So I would say that the derivative of that point is a positive number. And as we progress past the peak, we're going to find that these points over here have a negative slope. So the value of their derivative is actually going to be negative as well. But if I took the derivative at every single point in this function, and then I created a new function out of those, I would find that it would look something like this, where it's positive to the left of the peak of the original function, but it's negative afterwards. And that would give me my first derivative of f of x in this case, or f prime of x. And that's all it is visually. But unfortunately for economics, normally just doing it visually isn't good enough. We have to be able to do it mathematically as well. So if we were looking at this function mathematically, it would look something like this, where it's this complicated formula, the limit as h approaches 0 of f of x plus h minus f of x, all of that divided by x plus h minus x. Or I've simplified it on the right side. I've gotten rid of the x's in the denominator because they cancel out. But the reason why I'm showing you this is that this is actually just the slope function. All it is it is the change in our function values. The numerator is just delta f of x, where x is increased by h, and the denominator is just our change in x. All we are doing to figure out the derivative of our function is we're making that distance between x and h arbitrarily small. And that's what that limit means. We're letting h approach 0. So x and h are approaching the same value. And that's really neat because we're going to get rid of those precision errors. Like I was saying back with the price elasticity demand, when we jump a whole dollar in that, we can get some error whether we're going from $5 to $6 or $6 to $5. But if we're going the smallest distance possible, it's really not going to matter which direction we're moving. We're going to get a very accurate measurement at that point. So anyways, getting into the practical aspect of it, we're going to use derivatives primarily in two ways in economics. The first is conversion to marginals. So basically, we can take any variable in economics and convert it from its total to its marginal by just taking the derivative of its base function. So those are examples like marginal revenue, marginal cost, marginal utility, and it goes on. You're going to calculate more marginals than you ever thought existed. And you always define new ones. That's part of the fun of being a researcher. We figure out new types of marginals that we can interpret. The other one is a maximization or minimization problem. And honestly, I think this is where we're going to use them more often. But basically, if we take a derivative and we set it equal to 0, that's going to tell us whether we have the maximum or a minimum of the function. And just because that works, setting it equal to 0, is because the rate of change of a function is 0 at its maximum or its minimum. So it's just like this right here. Going back to our function, at that very top, if I took the derivative at that point, you'll see that you get a flat line. Now, the slope of that line is going to be 0, and that just means that it's not changing. So that is going to tell us that we have this extreme point right here. The catch, though, is that when you set a single variable derivative equal to 0, it's not actually going to tell you whether you have a maximum or a minimum, just that it's one of them. And in fact, it can't tell the difference between a maximum or a minimum. So in order to figure out which of those that we have, whether it's a maximum or a minimum, we have to actually take a look at the second derivative function, which we would call f double prime of x. And all that is it's the derivative of the derivative. And we're going to use the exact same steps to calculate it as before. And we're going to get into how we calculate those in the next video. So don't worry about how we actually calculate these. But anyways, the sign of our second derivative is going to tell us whether we have a maximum or a minimum. So if the second derivative is positive, that's going to correspond with a minimum. But if the second derivative is negative, that's going to correspond with a maximum. So let's actually take a look at this again. Going back to our original function, as we can see this first derivative, the red line right there, that has a consistent downward slope. In fact, it is a constant slope. It's constantly decreasing. So if I calculate a derivative of that function, I'm going to have a consistently negative number for f double prime of x. And because that number is negative, that allows me to prove that I have a maximum in this situation. Now, as a quick note, this only works for single variables. If we have multiple variables, we're going to need to use some other techniques that we'll talk about later on in these video series. But this will work for any single variable situation. Depending on the sign of our second derivative, that will tell us if we have a maximum or a minimum. But anyways, that's actually all for this first video. Thank you for watching.